In this video, we will factor polynomials using the pattern for difference of squares. So let's look a little bit at expanding these few examples. So I'm multiplying the binomial x plus 4 times x minus 4. When I expand that, it looks like this first x times x minus 4, and this 4 times x minus 4. Then when I distribute, it looks like x squared minus 4x plus 4x minus 16. These middle two terms will actually cancel away, so I'm just going to be left with x squared minus 16. Notice that this is a difference of two perfect squares. Notice 5x plus 1 times 5x minus 1. When I expand that and multiply, notice those middle two terms will cancel, and I'm left with 25x squared minus 1. Once again, a difference, which means subtraction, of two perfect squares. For 2a plus 3b times 2a minus 3b, I have the expansion here, this first 2a times the second binomial, plus 3b times the second binomial. When I expand that, I get 4a squared minus 6ab plus 6ab minus 9b squared. Negative 6ab plus 6ab cancels away, and I'm left with 4a squared minus 9b squared. All of these over here in this column are difference of squares. Difference means subtraction, and a perfect square means something times itself got me that term. So x times x got me x squared. 4 times 4 gave me the 16. 25x squared, what multiplied together to get that? Well, 5x times itself got me 25x squared. And 1 times itself got me this 1 here. So hopefully you guys see the pattern here. Notice how the binomials look almost exactly the same, except we have one positive and one negative inside those sets of parentheses, inside those binomials. So that's the type of multiplication that gives us a difference of squares for our polynomial. Well, remember, for factoring, we're trying to work backwards. So we would start over here and need to get these as our factored answer. So what's the pattern? If we recognize a difference of two squares, we know that we would have started with the same binomials but different signs. So for a squared minus b squared, we would end up with a plus b times a minus b. And we get the a and b by taking the square root. So let's look at a few examples. If I have a squared minus 4, I recognize right away that I have a difference of two perfect squares, because I know a times itself gives me a squared, and 2 times itself gives me 4. So that's how I know what my two terms are in my binomial. I know a times itself gives me a squared, 2 times itself gives me 4. Those are the terms, and then I have opposite signs. Now for c squared minus 100, I recognize that I have subtraction, which means the difference. I know that c squared is really c times itself, and 100 is really 10 times itself. So my terms are c minus 10 and c plus 10. Notice that it doesn't matter whether I write the binomial with the positive or the negative first. I'll still get the result back when I check my work. These two are on your own. Let's take a look here. Is this a difference of squares? We need to ask ourselves that question each time. So 81, well, that's 9 times itself, and x squared is x times itself, and we have that subtraction, which means the difference. So yes, this follows that pattern. So what would have gotten 81? It would have been 9 times 9 Notice how the 81 is first, so the 9 has to be the first term in my binomials. X times itself gave me x squared, so that becomes the second term in binomials. And I have a positive and a negative. Here I have 25x squared minus 49. Once again, is this a difference of squares? We have the difference for the subtraction. What times itself gives us 49? Well, that's 7 times itself. 7 squared is 49. 25x squared, well, 5x times itself would give me 25x squared. So this is a difference of two perfect squares. The thing times itself is what goes in the binomial. So what did we have to multiply to get 25x squared? 5x times itself. And what did we have to multiply by itself to get 49? 7 times itself. And we have our positive and negative pattern. These two are on your own. Next, we have x squared minus 81y squared. First, check to make sure it's a difference of squares. I have the negative, so that's the difference. X squared is x times itself. 81y squared would be 9y times itself, which means my two binomials have an x and 9y, and then opposite signs. Here I have x squared, y squared, and 1. What times itself would give me x squared, y squared? Well, that would be xy. 1, well, is 1 times itself. So this is a difference of squares, so we know we can follow that pattern. xy times itself gives me x squared, y squared. 1 times itself gives me that negative 1. These two are on your own. Right here, I have k to the 6th minus 16. So first we have to recognize, is this a difference of squares? So we know 16 is definitely a perfect square because that's 4 times 4. But we need to ask ourselves, what squared is k to the 6th power? Well, working backwards from our exponent rules, we know the way to get a 6 here would be to raise k cubed to the power of 2, because we would multiply those exponents together and get k to the 6th. So it is a difference of squares. K cubed squared gives me k to the 6th. So that looks like k cubed plus 4 and k cubed minus 4 when we follow that difference of squares pattern. What about here? We have 64m to the 4th minus 9n squared. Well, with the coefficients, we know those are perfect squares, 64 and 9. 64 is 8 times itself, 9 is 3 times itself. Now, what about these? M to the 4th. What times itself would give you m to the 4th? Well, m squared times m squared would be m to the 4th, and that is something times itself, which is squaring it. N squared would be n times n. So we have 8m squared plus 3n, 8m squared minus 3n. These last two problems are on your own.